Hello, today we're going to go over polar and non-polar molecules and how to determine whether or not a molecule is polar or non-polar. So in order to really explain how to do this, there are a couple of topics we need to review. Specifically, we'll go over electronegativity and then how to apply that to determine bond polarity. Then we're going to go over Vesper theory, and finally we'll pull all of that together to get to the main attraction or molecular polarity. So, starting with that first topic, electronegativity. Electronegativity is the tendency of an atom to attract the bonds in a pair of electrons, the electrons in a bonded pair towards itself. So with two atoms bonded together, one of them, if it's more electronegative, will pull those electrons closer to itself. And so the more electronegative atom will pull electrons more, and electronegativity has a number associated with it for every atom, and this can be found on that interactive periodic table at ptable.com. But roughly the trend is that electronegativity increases as you go up the periodic table, and it increases also as you go across towards the right on the periodic table. So atoms down here in that lower left-hand corner are the least electronegative atoms, and then atoms up here in the upper right-hand corner are the most electronegative atoms, with fluorine being the absolute most electronegative atom on the periodic table. So I have some examples listed: carbon, nitrogen, oxygen, and fluorine. These are all on the same row of the periodic table, and as you go from carbon to fluorine, the electronegativity increases. So carbon's 2.55, nitrogen is 3.04, oxygen has an electronegativity value of 3.44, and then finally fluorine has an electronegativity value of 3.98, which is the most electronegative atom on the periodic table. So that's the trend of electronegativity, and we use that to figure out bond polarity. So bond polarity is the separation of electric charge along a bond. It's also referred to as a dipole moment. So again, as these two atoms are bonded together, if one of those atoms is more electronegative than the other, it's going to pull those electrons in that bond closer to it. So there'll be more electrons on one side than on the other. So that more electronegative atom will start to develop something called a partial charge. So it'll be partially negative because there's a greater amount of electron density by it, whereas that other atom will start to become partially positive because there's less electron density over there. And so this is called a dipole moment, also just bond polarity. So it's based on the electronegativity. A very electronegative atom will pull electrons towards it, and you can determine whether or not a bond is polar or not by comparing the electronegativity values of the two atoms. So what you'll do is you'll just take the smaller electronegativity number, or the electronegativity number value of the less electronegative number, the less electronegative atom, and you'll subtract it from the greater electronegativity value, or the electronegativity value of the more electronegative atom. So for example, in a hydrogen-fluorine bond, you would take the electronegativity of hydrogen and subtract it from the electronegativity of fluorine, because fluorine is more electronegative than hydrogen. But once you have done that subtraction, you'll then compare it to this table. So if the difference in electronegativity was between 0 and 0.4, we call that a non-polar covalent bond. So even though a value of about 0.3 or 0.4 is still a slight dipole, it's not a very significant dipole. So we'd still kind of consider those as being roughly equally shared. So it's non-polar covalent. Those electrons are either equally shared or roughly equally shared, so there's not much of a dipole. On the other hand, between 0.4 and 1.8, this is what we would call polar covalence. Those electrons are still being shared, but as the atom becomes more electronegative, they're being pulled in one direction more and more. So as you go from 0.4 to 1.8, the difference in electronegativity is increasing. That bond is becoming more and more polar. And finally, once we go past a difference of 1.8, that's where we get to something called an ionic bond. So in this case, that atom is pulling those electrons towards it so much that it just takes them. It strips them away from that less electronegative atom completely, and we get full charges. So the more electronegative atom would be fully negative, the less electronegative atom would be fully positive. So it's called an ionic bond, but that bond is kind of in quotations because since those electrons have been fully stripped, they're not really bonded together anymore. Rather, they have something called an electrostatic attraction. So those two charges, fully positive and fully negative, they have a strong attraction because they're unlike charges, and unlike charges attract each other. So it's a strong attraction, not technically a bond. So that's an ionic character. So kind of put that in your back pocket because we're going to be using that later, but kind of shifting gears a little, we're going to talk about VSEPR theory. So VSEPR theory, or valence shell electron pair repulsion theory, it's this theory that allows us to predict the geometry of a molecule based on the number of electron pairs surrounding that central atom. So we have a central atom, and it will have electron pairs around it. They'll either be bonds or lone pairs, but they're going to try to surround it in a way that will maximize the distance between them, because electrons are all negatively charged, so that the bonds are going to repel each other, and they're going to try to arrange themselves to be as far apart from each other as possible. So the most simple molecule, other than just a bond, but a bond would obviously be linear because it's just two things attached. The most simple molecule would be one that has two electron-rich areas surrounding the central atom. So it would be an atom bonded to two other things. And the furthest apart those electron-rich areas can get would be 180 degrees, so on opposite side of that central atom. It would be 180 degrees apart, and we would call that linear. So in class, we talked about something called electron pair geometry and molecular geometry. Electron pair geometry considers all of those electron-rich areas to be roughly equal, and then molecular geometry deals with lone pairs, and they kind of separate lone pairs from bonded pairs. And we'll get more into the difference between those for the next examples, because as you can see, when there's two electron-rich areas, it would be two bonds 180 degrees apart, or linear. If one of those was replaced with a lone pair, then it would just be a bond between two atoms, which would obviously be linear as well. So that's two electron-rich areas. So building from there, we then move on to something that has three electron areas. So with those three electron areas, they're going to arrange themselves around that central atom, again, as far apart as possible. And that would lead to those bonds being about 120 degrees apart. And it's a flat molecule. So it's arranged in the plane of this sheet of paper, and it's kind of like a triangle. So that gets us to our electron pair geometry, trigonal planar, which makes sense because it's these three bonds arranged in a plane. But we can get a little bit more specific if one of those bonds is replaced with a lone pair, which would bring us to the molecular geometry. So again, the molecular geometry with no lone pairs would also be trigonoplanar, but if we replace it with a lone pair, we get to this molecule, and this would be called bent. Makes sense, it's just in the plane of the board, but instead of being linear, it's bent. The bond angle would be still roughly 120 degrees, but now instead of a third bond here, it's a lone pair. So that's with 3 electron areas. Building up from that, we get to 4 electron areas. So this is where the molecule starts to get a little bit more complicated. It's no longer completely flat, it becomes more three-dimensional. So you can see that here. These 2 electron areas are what I would call in the plane of this paper. So it's going up and then at an angle here. But these 2 guys are not. So this guy I have drawn as kind of a wedge or a very, very dark line. That's to indicate that this bond or this electron area isn't flat in the plane of this paper, but it's kind of coming out. So it's coming towards the screen a little bit. Whereas this guy right here, I have drawn as this dashed line. That's going to indicate that instead of being flat or coming out, it's going into this paper. So going in, coming out in the plane. These bonds are all about 109.5 degrees apart. If all of these are bonded electrons, we get to this electron pair geometry, and that would be called tetrahedral. It's tetrahedral because if you look at it, there's kind of 4 different planes, like a tetrahedron. But again, just kind of think of it as 4 bonds. 2 of them are in the plane, one's coming out, and one's going in. We then, again, can get more specific. So if they're all bonds, then the molecular geometry would be tetrahedral as well, but it changes as we start replacing those individual bonds with lone pairs. So if we replace one of those bonds with a lone pair, we get to this structure where these 2 bonds are still in the plane of the paper, but this guy is coming out. Not coming out directly straight, but kind of at an angle with that lone pair there. So this is where those lone pairs will become important, because if you look at this previous thing, there's 3 bonded pairs, but it's flat because there's no lone pairs to impact. In this case, those it has 3 bonds, but it's not flat because that lone pair is still there, and so it's still impacting the shape. It is, rather than being flat, it is taking that molecule and kind of pushing it down like that. So it has a shape called trigonal pyramidal, because if you kind of put it on, you can kind of put it on the ground and it looks like a pyramid that is being dictated by this lone pair. The next possibility is to have 2 lone pairs. So just taking this guy and replacing it with a lone pair, and we get to this shape. These 2 bonds are still in the plane of the board. These 2 electrons would be in these areas. So one lone pair is kind of coming out, the other lone pair is kind of going in, and it's creating this bent shape. Another comparison to make, this guy has a bent shape, but it only has 1 lone pair. So that bond angle is about 120 degrees. This guy is also bent, but it has 2 lone pairs. So that bond angle is still going to be further suppressed. So it's still about 109.5 degrees. That can kind of change a little bit depending on what the specific bond is, but it would still be about 109.5 degrees. So that's 4 electron-rich areas. The next possibility is 5 electron-rich areas. And the way that overall molecule looks, it kind of looks like if we took a linear molecule and combined it with the trigonal planar molecule, And so what I mean by that is it has, so these two atoms are arranged above and below that central atom in a linear fashion. And then the next three atoms are arranged around that central atom in a plane like a triangle. So this molecule is called trigonal bipyramidal. These three atoms that are around the middle have bond angles of 120 degrees because it's that trigonal planar feature. But these guys are 180 degrees apart or 90 degrees with each of these individual guys. So that's the electron pair geometry. Again, we can get more specific as we add more lone pairs. No lone pairs would still be trigonal bipyramidal in the molecular geometry, but if we replace one of those bonds, so this guy, with a lone pair, we get to this kind of structure, and this is called a sawhorse or a seesaw. And the reason for that name is just if you turn it a little bit, it looks exactly like a seesaw, or roughly like a seesaw. If we then take another one of those bonds, in this case this guy, and replace it with a lone pair, we're getting to a molecule that is referred to as T-shaped, so a molecular geometry called T-shaped. Again, it's obvious because it looks like a T. And then lastly, if we replace this guy with another lone pair, we get to a linear shape. So those are the possible electron pair geometry and molecular geometry of something with 5 electron-rich areas. The last possibility is something with 6 electron-rich areas. So roughly speaking, all of those electron areas are going to arrange itself one above and below in kind of like a linear fashion, just like before. But now that central atom isn't going to be surrounded by a triangle shape. It's kind of like a square. So a line here and a line here. It looks kind of like that, the coordinate system from math. It's just like that. So this is called an octahedral. So that octahedral with the 6 bonds would be the electron pair geometry, or if all of those electron-rich areas are bonds, also the molecular geometry. Now, going through and replacing bonds with lone pair, if we replace this bond right here with a lone pair, so now it has 5 bonding areas and 1 lone pair, it will take on this shape, which is called a square pyramid. So that lone pair will be at the bottom. Those next 4 will still be arranged in a plane around it, and then there will be another bond coming out from the top. The next possibility would be replacing another bond with a lone pair, and that would get to this shape. So 4 bonds, kind of in the shape of a square in the plane with 2 lone pairs. That's called square planar. Makes sense because it's square shaped in a single plane. Moving forward and replacing another bond with a lone pair, we get to another possible orientation for a T-shaped molecule. So this is called T-shaped. Over here is called T-shaped. And unlike before, when the number of lone pairs changed the angles, in this case, it is not. They have the same bond angles. But then we're once more removing another bond with a lone pair, we get back to that linear shape. So that's determining molecular shape. So keep that in mind and then bring back all of what we reviewed with electronegativity and bond polarity, and we're going to combine all of that to figure out molecular polarity. So a molecule is polar if it has polar bonds that are arranged asymmetrically. So what I mean by that is the polar bonds aren't symmetric. They're not pointing in equally opposite directions. They're either pointing in the same direction or slightly the same direction. And so if they're not symmetric, they don't cancel out, and I'll get to what it means to cancel out in a little bit. But that's how you have a polar molecule. To have a nonpolar molecule, you would have either no polar bonds at all, which is kind of obvious. If none of the bonds in a molecule are polar, then the molecule can't be polar. But you can also still have a nonpolar molecule with polar bonds that are symmetrically arranged. So that would be two polar bonds that are kind of pointing in opposite directions. As one pulls electrons this way, the other one's pulling electrons that way. So they kind of cancel out, which creates a nonpolar molecule overall. So to determine whether or not a molecule is polar, you need to first draw the molecule in its correct Vesper shape. So you need to be able to think about it three-dimensionally. The next thing you're going to do is look at all of the individual bonds in that molecule and determine whether or not the individual bonds are polar or nonpolar. Once you've determined that, you will then decide if the dipoles or those polar bonds cancel. So you'll have to look at where they're oriented in space. And if those polar bonds cancel, it's a nonpolar molecule, or if there are no polar bonds at all, it's also nonpolar. But if those polar bonds do not cancel, then you're going to have a polar molecule. So here are some examples. This first example, CH4, so carbon bonded to 4 hydrogens. That would bring us to this shape. So a carbon bonded to 4 hydrogens, so 4 electron-rich areas. That's that tetrahedral shape. So carbon bonded to 4 hydrogens, these guys in the plane, this coming out, this going in. The difference in electronegativity between carbon and hydrogen is very little. So the carbon-hydrogen bond is nonpolar. Since all of these are carbon-hydrogen bonds, there are no polar bonds. This is an overall nonpolar molecule. My second example is CH2Cl2, so a carbon that's bonded to 2 hydrogens and 2 chlorine atoms. So here we have those 2 carbon-hydrogen bonds. Once more would be nonpolar because the difference in electronegativity is very low. But now we have these 2 carbon-chlorine bonds. The difference in electronegativity between carbon and chlorine is pretty great. So these are going to be polar bonds. You can show this bond polarity with this arrow. This is called a dipole arrow. What you do is you just draw the arrow towards the more electronegative atom, and then you put a little cross at the end. It's kind of easy to remember the direction because this cross is going to be near the less electronegative atom or the atom that's going to be electropositive. So it's got a little partially positive charge. We put the little plus sign near it. So we've got these 2 polar atoms. This guy's coming out of the page, this guy's coming into the page, but they're not linear from each other. So even though this one's coming out and this one's going in, they're not directly opposite of each other. They're still roughly going in this downward direction right here. So we have these 2 polar bonds. They're not canceling because they're both roughly going in the same direction. This would be then a polar molecule. So the electron density of this molecule is going to be pulled this way. So these guys would be partially negative, and that would leave a partially positive area over here. So this molecule would have an overall dipole of going this direction. My third example is CCl4, or a carbon bonded to 4 chlorine atoms. So once more, that carbon-chlorine bond is going to be polar. So it has these 4 polar bonds. But if you look closely at this molecule, those bonds are all roughly pulling equally. So if you look at this bond, it has a dipole going up, and then it has these 3 going downward. And then if you rotate it, this atom has the same situation, pulling this way, and then these 3 pulling away. All of those dipoles are being pulled roughly equally, so these all will ultimately cancel out. So it has 4 polar bonds, but they're canceling out. So this molecule is nonpolar overall. My last two examples are comparing H2O and CO2. Both of those atoms have, both of these molecules have 3 atoms, but the polarity is very different because of their shape. So looking at H2O, or water, it's oxygen that's bonded to 2 hydrogens, and that would leave 2 lone pairs left out. So looking back at that 4 electron area VSEPR theory, we come down to this molecular geometry of bent. So 2 bonds and then 2 lone pairs. So it's this bent molecule. The oxygen-hydrogen bond is fairly polar because the difference in electronegativity is pretty great. So it's going to have this polarity going up like this and then up like that. So they're roughly going the same direction because of its bent shape. They're not going directly towards each other. So because of that, it has 2 polar bonds. They're not canceling out. So this molecule is polar overall, and the overall dipole of the molecule would then be going up like this. But looking at carbon dioxide, that's different. So it's a carbon with 2 bonds arranged next to it, but because of the valence electrons of carbon, it doesn't have those 2 lone pairs like oxygen did. It doesn't have any lone pairs. So it's just those 2 electron areas. And recall that would make the molecule let me find it. Yep, that would make the molecule linear. So it's a linear molecule. This carbon-oxygen bond is polar, so each of these bonds are individually polar, but one bond is pulling it this way, the other bond is pulling it this way, so it's kind of like a tug of war, and ultimately those 2 dipole moments will cancel. So again, we have 2 polar bonds, but they're canceling, so that molecule is nonpolar overall. So that is how you determine whether or not a molecule is polar. Shoot me any questions if you have them, and I hope you're staying safe and healthy.